In this brief lecture, I wanted to finish off chapter 9 of the book and talk about angular momentum. Angular momentum, L, is given by mass of an object times r times tangential velocity. So if we have an object of mass m, which has a tangential velocity v, moving in a circular path of radius r, then the angular momentum is mrv. We're going to do a full treatment of angular momentum in chapter 13, so I just wanted to mention it in this chapter since the book covers it, so I wanted to introduce the angular momentum. And similarly, just like linear momentum, if tangential force Ft is 0, then that means that there is no tangential acceleration, i.e. The angular, well, Vt remains constant, which means that angular momentum initial will equal angular momentum final. So conservation of angular momentum applies if provided tangential any tangential force acting on the object is 0. If there is tangential force acting on the object, then the angular momentum will not be conserved. So for example, if you have um, if you have an ice skater that is spinning about a vertical axis while she's holding out her hands, so she's spinning this way. This is radius r, and let's say she's holding two weights of m and m on each hand, and if the velocity by which she is spinning is v tangential, then her angular momentum is given by the sum of the two angular momenta, which in this case becomes 2mr v tangential, because the angular momentum for each mass is mrvt, and there are two of them at each hand, in each hand. Now, if she were to pull her arms in, then the masses would be closer to the axis of rotation. Alright, so let's call this r initial, and this would be r final. Masses haven't changed, and so this would be angular momentum initial, this is r initial, and v tangential initial, of course. Now angular momentum final would be 2 mass r final times v tangential final, and since there is no tangential force acting on our skater, she's skating on ice, so it's a frictionless surface, so there's no tangential force acting on, so Ft on the masses, Ft is 0, therefore we could argue that Li is equal to Lf, i.e. Twice mri v tangential initial is equal to twice mr final v tangential final. Now from here you see that since r final is less than r initial, that means that v tangential final must be greater than v tangential initial. So the ice skater, by pulling her arms in, she's able to spin faster than when she had her arms stretched out. There is one of the homework problems involves a seesaw. If I'm not mistaken, there is two masses, two people standing, M1 and M2, and this distance is given as x1, this distance is given as x2, and we are told that I guess one of the persons, M2, pushes the board downwards, and we are asked to find the velocity of the other mass. What you need to do here is, since we're talking about rotational motion, you need to use angular momentum. So first of all, the F tangential, net F tangential, sum of F tangential is 0 on the system, so we make use of that fact to say that angular momentum initial must equal angular momentum final, and angular momentum initial is 0 because in the initial situation the two persons are standing at rest on the seesaw. Therefore L final must equal 0. Now L final is mass 1 x1 times v velocity tangential 1 plus mass 2 x2 velocity tangential 2. So the sum of the two must equal 0, and I believe the velocity for one of the persons is given, so it's a trivial matter to figure out the other velocity. But let's say the way to go about solving a problem like this is by using conservation of angular momentum argument. As far as other examples, that there was another homework problem that involved a person standing on a cart. Now we have person standing on a cart, so the cart has a mass, person has a mass, and let's say the cart has initial velocity and the person standing at rest with respect to the cart initially, and then the person starts running towards the other end of the cart with some velocity. So I'm going to call it velocity person prime, because we are given in the problem, we are given the velocity of the person with respect to the cart, and we are asked to find velocity of the cart final. So velocity of person with respect to cart initial is 0, velocity of person with respect to cart final we are given. So we are given this value, we are given this value, we of course know this, so this is what we are trying to figure out, velocity of the cart final. Now everything takes place on a frictionless surface, so if friction is 0, so since friction is 0, then we know that momentum initial must equal momentum final. Now momentum initial is the momentum of the person initial plus momentum of the cart initial, which must equal momentum of person final plus momentum of the cart final. Because you are what you need to do is define your isolated system, and an isolated system of course includes both the person and the cart together. Now to calculate momentum of the cart, well, that's simple. Momentum of the cart initial is simply mass of the cart times velocity of the cart initial. That's this term right there. Momentum of the cart final, that's simple too. That's momentum of the car, mass of the cart times velocity of the cart final. But you have to be a little bit careful with the momentum of the person, because the velocity for the person is given with respect to the cart. So from it's from a reference frame which is at rest. So if you bring your reference frame out here, then velocity of the person is equal to the velocity, the relative velocity that the person has with respect to the cart, of course, plus velocity of the cart. Okay, so velocity of the person initial is the relative velocity that the person has plus VCI. Similarly, velocity of the person final is velocity of the cart final plus so let me rewrite this, is equal to velocity of the person final with respect to the cart plus velocity of the cart final. So you need to use the Galilean transfer functions to calculate the momentum of the person final and initial. So here final, and we have mass of the person, velocity of the person initial. So this term here is that, and this term right there is this. So you use the Galilean transfer function to calculate the velocity of the person in a stationary reference frame. So that was one clue I wanted to give you with respect to one of the homework problems. Now, oops, sorry, I apologize. Now the last problem I wanted to give you a hint on is the one where we have a target and we fire a bullet towards it. The bullet has mass bullet and it has some velocity bullet initial. It penetrates through the target and emerges with some velocity bullet final. The target is on a frictionless surface. That's good. That means the impulse is zero, so we can use conservation of momentum theorem. And velocity of target initial is zero, and we know what the mass of the target is, and we are interested in finding out what the velocity of the target final is. So we need to figure that out, and we're also asked to find I believe the force, average force that the target exerts on the bullet to slow it down, as well as the time that it takes for the bullet to travel through the target, which we are told is d meters long. So we know the thickness of the target. Now, first of all, what I'm going to do is define my system, my isolated system, to include the bullet and the target. So the red is my before scenario and blue is my after scenario. So momentum initial, and I have momentum final. Momentum initial is mass of the bullet, velocity of the bullet initial, plus mass of the target, velocity of the target initial. Momentum final is mass of the bullet, velocity of bullet final, plus mass of the target, velocity of the target final. And these two must be equal since impulse is zero because we have a frictionless surface. Alright? So initial momentum equals final momentum. So we can figure out what delta P, or change in momentum of the bullet, is. So change in momentum of the bullet. Actually, I'm sorry, before we even go there. Alright, so that's one expression that we can derive. And we don't know. From here you can figure out the velocity of the target, velocity of the target final. Now we're also asked to figure out what the average force is that the target exerts on the bullet to slow it down. Well, we know that the velocity of the bullet goes from velocity b initial to velocity bullet final. So there is a negative acceleration involved while it passes through the target. Using the kinematic equation, velocity final squared is equal to velocity initial, bullet initial squared, plus twice acceleration times the distance that it travels, d. You can now come up with a value for a. So now you can figure out what a is, because you know final velocity, you know initial velocity, and the thickness is given, so it's a trivial matter to figure a out. If you know the a, which is the acceleration or deceleration of the bullet, then the force, average force on the bullet, is equal to mass of the bullet times that a. Just bear in mind that a is a negative number though, because we have deceleration, so the force is going to be a negative force, which makes sense. The force on the bullet is going to be in the opposite direction to its motions because it's slowing it down. So that's how you figure out the average force. Now, having figured out the average force, use impulse momentum theorem. It says impulse on the bullet is equal to change in momentum of the bullet. Change in momentum of the bullet is simply mass of the bullet times velocity of the bullet final minus velocity of the bullet initial. So you can figure out the right hand side of this equation. That equals the impulse on the bullet, which is equal to average force times the time that force acts on the bullet. And average force you just figured out from up here, so now this equation enables you to figure out delta t, the time that it takes for the bullet to pass through the target. And as I said initially, the way to figure out the final velocity of the target is by choosing your system to be made up of bullet and the target together. You call it your isolated system, and equate the final and initial momenta. Okay, so these are just a few examples that I wanted to give you hints on in solving the homework problems, and in the next lecture we'll discuss energy, gravitational energy, spring energy, and of course kinetic energy.